Okay, welcome back. This is second lesson on arithmetic sequences. And before we dive into today's problem, okay, I'm going to write it in a minute. Let's go ahead and look at, again, the definition of a sequence and definition of a function. Okay, so definition of a sequence is that what? A sequence is a function, can be graphed, whose domain is the set of natural numbers. Now, not a set, but the set. The natural numbers are a specific set of numbers, okay? There is just one set of natural numbers, and that symbol for natural numbers is symbol capital N with two lines. It's a special symbol, okay? And let's look again at the set of natural numbers. The set of natural numbers are the counting numbers 1, 2, 3, 4. It's imperative that you watch the previous video before you watch this video. Okay, so the first video on arithmetic sequences needs to be watched before you watch this video, or you might get a little bit lost. 5, and then what? Dot, dot, dot. And again, the set of integers, just recapping, set of integers. This is capital Z, again, two lines. It's a special symbol, represents the set. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. And we are looking at, again, both of these sets are infinite. The set of natural numbers goes on forever. The counting numbers, simple numbers. Big gaps, though. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that there are no negative numbers in the set of natural numbers. Okay, -5 is not a natural number. And notice that 0 is not in the natural numbers. Okay, the natural numbers are just the counting numbers. Also, there are no decimal values like 2.5 or 3.7. Okay, these numbers are not in the set of natural numbers. There are gaps. We are skipping all the numbers between 2 and 3. Okay, now, the set of integers, notice, are all of the natural numbers, their opposites, and 0. Okay, so we have all of the natural numbers, 1, 2, 3, 4, 5, all of the their opposites, -1, -2, -3, and so on and so forth, and we have 0. Again, there are gaps. The number -1.5 is not in the set of integers. -3.7 is not in the set of integers. It is just the numbers. If we look on the number line as the x-axis here, 0, 1, 2, 3, -1, -2, -3. The natural numbers, the top set, are just the numbers 1, 2, 3, skipping all numbers between. And the integers include the naturals, 0, and all their opposites. Okay, -1, -2, -3 again. -1.5 is not an integer. And 2.5 is neither an integer nor is it a natural number. Okay, so we're just again looking at broken, or think of this as gaps between your values. Lots of numbers missing. Okay, now, definition of a function. Again, definition of a function. Okay, what was that definition? Most important definition in this class, and this is what we're going to be looking at the rest of the semester, trying to understand what this definition says with respect to what we're studying. Definition of a function is a function is a set of ordered pairs. These are points. Set of ordered pairs of points on a graph. Set of ordered pairs in which each element of the domain maps to exactly one element in the range. Now I'm going to try to help you see a little bit, I guess, a concept of what this definition is saying today using these two sets of numbers. And we talked about in the last lesson that the set of natural numbers, if I asked you which set has more numbers, okay, and we look at these, and I told you that the set of natural numbers, the set of integers, have the same number of numbers. Okay, I'm going to show you that a function is used to prove this idea. I think this will intuitively make sense, but the function we're going to use is f of x equals x over 2 if x is even, you don't have to understand where this function comes from, but just accept that this will work, and I'll show you. 1 minus x if x is odd. Okay. Now, this is a piecewise function. We've talked about piecewise functions already. So we're going to use y equals, remember f of x is a representation of y equals x over 2 if x is even. And remember over here we have domain. Okay, domain. And we're going to use y equals 1 minus x over 2 if x is odd. Okay, so our domain. What's our domain? Our domain is going to be the set of natural numbers. Okay, natural numbers would be the domain. And the set of integers will be the range. Now notice that the definition of function says that each element, or we read this as every number, remember that element means number, every number in the domain maps to exactly one number in the range. So watch this. Okay, so we're going to map the set of natural numbers onto the set of integers and see that these two sets have the same number of numbers. At least intuitively this should make sense. So we're going to look at, first off, we're going to start with even. X is even. Notice this is our domain. So x is even. X is even. What are the even numbers in the set of, here, let me just write this out a little more. 5, 6, 7, ... Okay, so we're going to look at the even numbers in the domain. Again, our domain is the natural numbers. So we're looking at the even numbers, 2, 4, 6. Okay, so what is the first even? The first even is 2. So we're going to put this into the function. We're going to put 2 in for x. X is our domain. So we're going to write f of 2. Okay, and when x is even, or when our domain value is even, we're going to use x over 2. So 2 is going in for x. 2 is going in for x. We're going to get 2 over 2, which is 1. So we see that when x is 2, we get an output of 1. So 2 will map to 1 in the set of the integers. Now, we're going to go to the next even, 4. Okay, so f of 4. F of 4, we're going to use the x over 2. Notice that our x value is 4, so we're going to write 4 over 2. And 4 over 2 is 2. Okay, so our output is 2. So 4 will map to 2. Okay, now we're going to do 6. 6 is our next even, so we're going to find f of 6. Okay, we're still going to use x over 2, so we have 6 over 2, or 3. So our output is 3, so 6 will map to what? 6 will map to 3. So do you see that 2 will map to 1, 4 will map to 2, 6 will map to 3, so on and so forth. And what will the next value be? The next value in the domain will be 8. 8 will map to 4, and the next value will be 10. 10 will map to 5, etc., etc. Now let's look at the odds. Okay, so let's look at odds. So when x is odd, okay, so first we're going to identify what is our first odd in our domain. Our first odd is 1. I'm going to erase this. Okay, erase this. Okay, and this. Just looking at the odds now. So our first odd is 1. Okay, and we're going to put 1 in for x, using the expression 1 minus x over 2. So we're going to say f of 1, we're going to use the expression 1 minus x. So 1 will go in for x. We get 1 minus 1 over 2, which is 0 over 2, or 0. So we get an output of 0. So 1 will map to 0. Okay. And now we're going to do our next odd. Our next odd is 3. So we're going to do f of 3. Remember, when it's odd, we're going to use 1 minus x over 2. So we're going to put in 3 for x. We get 1 minus 3 over 2, which is negative 2 over 2, or negative 1. Okay, so 3 will map to what? 3 will map to negative 1. And now we're going to do 5, which is our next odd. F of 5 gives 1 minus 5 over 2, which is negative 4 over 2, or negative 2. So 5 will map to what? 5 will map to negative 2, and so on and so forth. 7 will map to what? 7 will map to negative 3. So this mapping that's going on, I want you guys to notice the definition of a function. In order for something to be a function, every number in the domain must map to exactly 1. Okay, so every number in the domain, remember our domain is a set of naturals, every number in the domain must map to exactly one number in the range. So is 1 mapping to one number? Yes, it's mapping to 0. Is 3 mapping to one number? Yes. Is 4 mapping to one number? Yes. Is 5 mapping to one number? Yes. Every number in the domain is mapping to exactly one number. 6 is mapping just to 3. Okay? And notice, your evens go on forever. So 2, 4, 6, 8, 10, 12 will take care of all of the positive numbers in the set of integers. Also, your odd numbers go on forever. 1, 3, 5, 7 go on forever. And this will take care of all the negative numbers, and it will take care of 0 in the set of integers. So do you see that every number in the set of integers can be mapped backwards to the set of natural numbers? Okay, so this is the beginning of what we call proof. To prove that these two sets have the same number of numbers, we call this cardinality, counting the number of numbers in a set. These two sets have the same number of numbers because both sets are said to be denumerable or countable. Okay, so we can count the numbers in this set. However, the set of real numbers is said to be uncountable. There are so many numbers in this set that you can never count them. In the set of real numbers, if you have 0.1, well, between 0.1 and 0.01, there are so many numbers between 0.1 and 0.01, for instance, 0.09, 0.099, 0.0999. Okay, there are so many numbers, 0.099999. There are so many numbers between 0.1 and 0.01 that they are uncountable. Okay? In fact, the real numbers has a much larger infinity, or a much larger number of numbers than the set of natural numbers or the set of integers. Although these sets are infinite, the set of naturals is an infinite set, the set of integers is an infinite set, these levels of infinity are smaller levels of infinity than we say the real numbers, much bigger set. So this is really kind of weird. But hopefully you see today, at least the concept of function means some sort of mapping between the domain and what? Between the domain and the range, in which every number in the domain is mapped to exactly one number in the range. And also you get a concept here of why these two sets have the same number of numbers. And what do we use to prove this? To prove that these sets have the same number of numbers, we use what? We use a function. Okay, so functions have many applications. Right? In fact, function is the way that we apply algebra to the real world out there. But even in math itself, to prove one thing in math, we use what? For instance, here we use what? Functions. So functions just have tremendous application. Why is this the most important definition in this class? The goal of this class is for you to study functions and to understand what is a function. Okay, now we see that a sequence is what? A sequence is a function. So sequence is definitely important. It is one of our functions. I should have made you guys put not just the 10 parent functions that I gave you, but I think next year I'm going to add 2 more. The arithmetic sequence and the geometric sequence, so that when you look on your parent functions list, you see here's your linear function. Okay, a linear function is a line. Okay, a linear function is a solid line, and then I'm going to give possibly arithmetic sequence. Arithmetic sequence is not a line, but follows a linear pattern of points that fall in the shape of a line, but they're not connected. Okay, they're broken. So arithmetic sequence looks like a line, but it's a set of broken points. Okay, so you see this immediately. Now, today's lesson, first problem we're going to look at, let me erase all this. Okay, a little bit different given information than you were given in the last video. Last video I gave you a list, or I gave you the range. Today you're going to have to find your list. So for instance, if I give you this information, what do you do if I write a sub 5 is equal to negative 11 and d equals negative 3? What do you do with this? Okay, how do we study this with respect to arithmetic sequence? Well, this is an arithmetic sequence. So what do we do to get started? Here, erase this. We need the space. Okay, so I say a sub 5 is negative 11, d equals negative 3. This looks like problems in your book. In fact, well, I don't have the book open right now, but a sub 5 equals negative 11. What is the goal here for you to accomplish? Well, let's write it in this format. Write a sub 5, negative 11. So put a sub 5 underneath negative 11. And I want you guys to write a sub 4. Well, before we do this, write a sub 6. Okay, so a sub 5 means position 5, or height at 5. What did we read this as? Height at 5 is what? Height at 5 is negative 11. We want to know what the height at 6 is, or what number in the range is in position 6. Okay, it also gives us some other piece of information, common difference. So it says the common difference is negative 3. Remember, arithmetic means what? Arithmetic means we are adding. And what are we adding? We are adding the common difference. Okay, so if the common difference is positive 3, you're adding 3. If the common difference is negative 3, you're adding negative 3. Okay, so to go to the next value in this, to go to the next value in the range, we are going to add what? We are going to add negative 3. So negative 11 plus negative 3. I want you to write plus negative 3. Okay, adding negative 3, you can think of this as subtracting 3. So negative 11 subtract 3. Negative 11 subtract 3 gives negative 14. But again, are we subtracting? No. What does arithmetic sequence? Arithmetic sequence means that we are doing what? We are adding. So, okay, so are you subtracting 3 or are you adding negative 3? If I asked you for the common difference, this is where the confusion comes in. No, the common difference is not 3. The common difference is negative 3. Why? Because we're asking what's being added. We are subtracting positive 3, but we are adding negative 3. So the question is, what are you adding? You're adding negative 3, and you can think of this in your head as subtracting 3. Okay, but the common difference is negative 3 because that is what we were adding. So we're adding negative 3 to go to the next term. Next term is negative 14, and the seventh, or the height at 7, add another negative 3, we get what? We get negative 17. So you see that going to the right, the values are going down. Okay, so they're going down by 3. Okay, to go backwards, think about it. If we're going down by 3 to go forward, or to the right, what are we going to do to go backwards? Okay, we're going to do the opposite. We're going to go up by 3 or add 3. So to go backwards is to add 3. What is the goal for this problem? I told you guys yesterday that step 1, or in the last video I said step 1 was to find the common difference. However, what is given in this problem? Okay, the common difference is given. Okay, so if they give you the common difference, the goal changes. Okay, so step 1, if they give you the common difference, step 1 will not be to find the common difference. Step 1 will be to find what? Step 1 will be to find a sub 1, or find the height at 1. Okay, so your step 1 becomes find a sub 1, or the height at 1. So we have to work backwards. Notice we have the height at 5, 6, and 7 now. We need to work backwards to what? Here's a sub 4, a sub 3, a sub 2, a sub 1, and we're going to work backwards. So if we're adding negative 3 to go to the right, we're going to add positive 3 to go to the left. Or if we're going down to the right, we're going up to the left. So add 3 to negative 11, we get what? Negative 8. The values are increasing. Add 3 again, we get what? Negative 5. Okay, add 3 again, we get negative 2. Add 3 again, we get positive 1. So again, adding negative 3 to go to the right, to go backwards, the opposite, add positive 3. Okay, so adding 3 gives negative 8, negative 5, negative 2, and 1. All right, so you found a sub 1. So step 2, I'll write it here. Step 2 was to graph, and graphing includes t-tables. So we're going to make a t-table, reminding you we're not using x and y, we're using what? N and a sub n. Draw a graph. Okay, this is our n-axis. Okay, the x-axis is n-axis, and we have a sub n here. Okay, so the y-axis is a sub n. Now, the domain. Okay, does the domain ever change? No. The domain for sequence is what? Domain for sequence is written here. A sequence is a function whose domain is a set of what? Natural numbers. Okay, so the domain is always a set of natural numbers, and these numbers are what? 1, 2, 3, 4. Put your dot, dot, dot. Okay, remember we use dot, dot, dot instead of an arrow on the graph, meaning that this goes on forever. And now our range. Circle the values in the list. Okay, this is your range. I want you to always circle these and label range. Okay, so our range values are what? Notice we read this as height at 1 is 1, height at 2 is negative 2, height at 3 is negative 5, height at 4 is negative 8. Remembering that a sub 4 is read as height at 4, and a sub n is read as height at what? Height at n. This will lead us into f of 2. When we deal with functions, f of 2, functional notation. Sequences are also functions, and we know this, but functional notation, f of 2 will be what? Height at 2. And f of x will mean what? Height at x. Okay, so just again, getting familiar with this. Erase this. I'm going to write at the top. We're using sequence. We're using a sub n for sequence, so a sub n is what? Height at n. Okay, now we're going to write our range, a sub n, or height at n. Height at 1 is what? Height at 1 is 1. Height at 2 is what? Negative 2. So we're writing the values in this list, the range. Negative 5, what else do we have? Negative 8. Put your dot, dot, dot. This means the value's going forever. Okay. And now I told you, do not change the scale on the n-axis. The n-axis will always stay the same. Why? Why will it stay the same? Or why will it always be units of 1? Because our domain, the n values, will always be the set of natural numbers. 1, 2, 3, 4, 5, 6, 7, etc. Now, the vertical scale, I said to change your vertical scale to the same units, or change your vertical scale, make your vertical scale the same as the common difference value. In this case, the common difference is -3. I'm talking absolute value of the common difference, so let's just think 3. So our vertical scale will be 3, 6, 9, 12, 15, and our negative scale follows the same pattern. So we have -3, -6, -9, -12, etc. And let's go ahead and graph our points. So we have the point 1, 1. Okay, point 1, 1 is here. The point 2, -2. The point 3, -5. And the point 4, -8. Okay. Question. Do our points form a line? No. We've talked about this. Why? Because the domain is just a set of natural numbers. Remember, is 2.5 in the domain? Is 2.5 in the domain? No. 2.5 is not in the domain, meaning that we don't have a value. We don't have a value at -3.5. Okay, so we don't have a value at -3.5. 2.5, -3.5 would be where? 2.5, -3.5 would be here. Make a very big point. Okay, 2.5, -3.5 would be here. Do we have a point located here? No. Why? Because 2.5 is not in the domain. Question, is 2.6 in the domain? No. So do we have a point down here for 2.6? No. Is 2.7 in the domain? No. So do we have a point down here? No. We do not have infinitely many points between any two points, so we do not connect. Remember, connecting points. When you connect points, you are graphing infinitely many numbers. We are not connecting points because our domain is a broken set of natural numbers. We have a height where? We have a height at 1. Okay, our height at 1 is 1, so at 1, we are at a height of 1. We have a height at 2. At 2, we are at what? -2. So at 2, we are at -2, at a height of -2 down here. At 3, we are at a height of what? -5. At 3, we are at a height of -5. And at 4, we are at a height of -8. So at 4, -8, and nothing in between. So, erasing this back out. And again, reminding you, are there ever points that, or do points lie to the left of the y-axis? Or will points ever lie to the left of the y-axis? No. Or a sub n axis, I should say. No. Why? Because we do not have negative values in the domain. Remembering that domain is what? Domain is an axis. We do not have -1, -2, -3, -4, -5 in the domain. Okay. Also, question, does this function have a y-intercept, or does it ever touch the y-axis? No. But this is a critical concept, so I'm going to erase this information. For every sequence that you put on the board, okay, why do we have to know a sub 1? Well, the key is this. We want to find the value that's actually before a sub 1, or the imaginary y-intercept. The imaginary value that's not actually part of the function, a sub 0. Go ahead and write a sub 0, and let's use the pattern. Going backwards is going up by 3. So -8, -5, -2, 1. Increasing by 3 again would put us where? At 4. So our imaginary point that's not actually part of this function is a sub 0 equals 4. Cross this out, reminding you, this is our imaginary. Go ahead and write imaginary. Imaginary, what I'm saying is it's not part of the function. Imaginary y-intercept, or the point that's not actually part of the function, which would represent, if this were a function in terms of a line or linear function, where would it cross the y-axis? So I want you to mark the location, a sub 0, 4. If it did exist, at 0 we would be at a height of what? 4. I want you to mark this point at 0, 4. Notice, why is this not part of the function? Okay, I want you to circle it, cross it out, and write not part of the function. And why is it not part of the function? Again, because notice the point 0, 4, we read this as the point 1, 1, the point 2, -2, the point 3, -5, the point 4, -8. Looking in the t table, you can see it. 1, 1, 2, -2, 3, -5, and 4, -8. We read this as the point 0, 4. Why is this not a point? Because 0 is not a natural number. Okay, 0 is not a natural number. 0 is not in the domain, so cross it out. Okay, put it in the t-table, but cross it out. This is the imaginary y-intercept. It doesn't actually exist as part of the function. But why is this important? This is important because it's going to save us a lot of time in finding the equation of this arithmetic sequence. Now, yesterday we talked about step 3. Step 3 was to find the equation, or to write the equation of the sequence. We're going to speed this up today. Well, No, we'll follow the same steps, but I want to talk about next lesson. We're speeding this up. Using this imaginary y-intercept, remember that what function is arithmetic sequence related to? Arithmetic sequence is related to linear function, and we say that this is what? This is a linear pattern. It's not a linear function. It is not a line, but it looks like a line. So we're going to use what we know about linear function to study arithmetic sequence. And so underneath this, a sub 0 equals 4, I want you to write y equals mx plus b. Okay? Now, we're going to write the equation of this sequence very, very quickly using this y equals mx plus b 4. Okay, so instead of y, we're using what? Variable a sub n. So underneath y, I want you to write a sub n. And underneath our slope, remember we said slope is the same as what? Slope is the same as common difference. I should write this here. The common difference was what? Negative 3. We said that slope is the same as what? Slope is the same as common difference. Notice our points. If this were a line, does it appear to have a positive or negative slope? Hopefully you say negative to go down. How far do we go down? Well, we go down 3, and we go right how far? We go right 1. So down 3, right 1. The rise is negative 3, and the run is what? The run is positive 1. So we get negative 3 over 1. If we thought of this in terms of slope, the slope would be negative 3. We said that the slope is the same as what? Slope is the same as common difference. Or common difference can be thought of as slope. Is it the same thing? No, but we use this analogy. Okay, now, so for slope, we're going to put what? The common difference value of negative 3. And instead of x, we're using variable what? Variable n. And instead of b, remember that b represents the y value of the y-intercept. Okay, instead of b, we're using the imaginary location of the y-intercept, which is what? Positive 4. And this is the equation of the sequence. The equation of the sequence is a sub n equals negative 3n plus 4, or we're looking at y equals mx plus b4. Now, yesterday I said we used point slope form yesterday, or in the last lesson. A sub n minus a sub k equals d times quantity n minus k. And again, we related this back to point slope form of a linear function. Y minus k equals m times quantity x minus h. Why is this important? Why don't we just write the equation this way? Okay, so I'm going to answer that now. We have to know how to find the equation of the sequence using the concept of point slope form, because it's not always possible to know the value of a sub 1. If it's not possible to know the value of a sub 1, then you would not be able to find the value of a sub 0. Remember, the a sub 0 is our trick to find this equation very quickly. So what happens when you cannot find a sub 1 and this imaginary a sub 0? Okay, what happens when you cannot find this? Well, you have to revert back to this form. Okay, so again, we need what? Two pieces of information to graph a line. We need a point and a slope. Okay, so same thing. For arithmetic sequence, we need a point, and let's pick a point here. Our point is going to be what? Point is going to be, I'm just picking a random point. How about a sub 4 equals negative 8? Don't use the first point. Use something different than the first. How about a sub 4 equals negative 8? So the emphasis being, you don't have to know a sub 1. You can use any of these points. So a sub 4 equals negative 8. That's right. A sub 4 equals negative 8. And our slope is the same as what? Common difference. So let's write d equals negative 3. Now, erasing this, if you are struggling to understand this, you're going to have to watch the last video, but I'm going to give you another example of how to write this. A sub 4 equals negative 8. Remember, we read this as the point 4, negative 8. Notice here, a sub 4 equals negative 8. We read this as the point 4, negative 8. It's in the t-table here. Now, do we write points this way? No. Instead of 4, negative 8, we write what? A sub 4 equals negative 8, and we read this as the point 4, negative 8. So this is proper form for sequences, is to write our points as a sub 4 equals negative 8 instead of an ordered pair. We read the point as 4, negative 8. Now, same thing. We're going to do the same thing with the arithmetic sequence form that we did with the point slope form of linear. So we're going to take the y value. Notice our y value is what? Negative 8. Y value is negative 8. We're going to put that next to y. Notice that our y is what? A sub n. Instead of writing y, we're going to write what? A sub n. And the opposite of the y value is what? Positive 8. So plus 8 equals, and now our slope or our common difference goes next to negative 3. Instead of x, we're using what? Instead of x, we're using n. and then opposite the x value. Since our x value is 4, or our n value is 4, opposite of 4 is what? Minus 4, and you've written the equation. You've written the equation with the original piece of information that you were given. The original piece of information that you were given was that a sub, well, I think it was actually a sub 5 equals negative 11, and a sub 4, I'm sorry, the common difference was negative 3. So without putting any of this on the board, you could have used these two pieces of information to write the equation. Let's write it with this information. Let's practice again. So let's write a sub n minus a sub k equals d times quantity n minus k, and let's put this information in using the point a sub 5 equals negative 11 and common difference is negative 3. These are the same thing. Watch. So we'd say y is a sub n, then opposite the y value. Since our y value is negative 11, what are we going to put in? We're going to put in what? Positive 11 equals common difference is negative 3, same thing as slope, so we're going to put negative 3 times quantity, not x, but rather n, then opposite the n values. If we have an n value of 5, we're going to put what? Minus 5. Now, so we have this equation. We also have the equation a sub n plus 8 equals negative 3n minus 4. I'm going to write this here. A sub n plus 8 equals negative 3n. Negative 3 times quantity n minus 4. And we're going to simplify each one of these equations. Solve each equation for a sub n, or get a sub n by itself. We're going to get a sub n by itself to get our y equals mx plus b form. And we're going to see that both equations give us the same thing. Watch. So we're going to start with take the negative 3 and distribute. We get a sub n plus 8 equals negative 3n plus 12. Move the 8. 8 becomes negative 8. We get a sub n equals negative 3n. 12 minus 8 is what? 4. Let's do it again. Okay, notice, take the negative 3, use distributive property here. We have a sub n plus 11 equals negative 3n. Negative 3 times negative 5 is positive 15. Take the 11, move it to the other side, it becomes what? Negative 11, cross it out, we get a sub n equals what? Negative 3n. 15 minus 11 is 4. So notice, we get the same thing. Same thing. Same thing. Okay, so all three equations are exactly the same. Does it matter which point we use? Does it matter whether we use a sub 4 is negative 8 or we use a sub 5 is negative 11? No, we get the same equation. Again, this concept of point-slope form, or relating this to the concept of point-slope form of linear, this equation is used when we do not know the value of a sub 1. Okay, so when we do not know the value of a sub 1, we can use this equation. Now, step 4, I'm running out of space. Step 4 was to find the height at 50. Okay, now height at 50. Height at 50 is written as what? A sub 50. Remember, height at 4 is negative 8. Height at 5 is negative 11. Height at 6 is negative 14. Height at 7 is negative 17. And how much work would it take to go all the way to the height at 50? Well, height at 7 is negative 17. We're going down by 3, so height at 8 will be negative 20. Height at 9 will be negative 23. Height at 10 will be negative 26, etc., etc., etc. But this would take a very, very long time. What is the equation useful? Or I should say, what is the equation used for? The equation is used to generate large terms in the range, or large values in the range, or heights at large n values. So let's go ahead and write the equation. A sub n equals negative 3n, we're using this equation, plus 4. Okay, and this will allow us to generate a height at 50 very quickly. So underneath a sub n, I want you to write a sub 50, okay, is equal to negative. Notice, what is replacing n? What is replacing n? Hopefully you say 50. Okay, so we're going to replace n with 50 here. So we're going to get negative 3 times 50 plus 4. Negative 3 times 50 is negative 150, plus 4 is negative 146. So we get a sub 50 equals negative 146. Now, we read this as the ordered pair 50, negative 146, but this is not how we write it. We write it as a sub 50 equals negative 146. And you can see that the height at 50 is negative 146. Or if we go 50 units out, look at this. The points are going down. Notice the points are going down concept of negative slope, if we go out to 50, at 4 we're at negative 8. At 5 we would be at negative 11. If we go all the way out to 50, way out here, where would we be? Way down where? At a height of negative 146. So way out at 50, we would be way down at negative 146. Makes sense. Okay, so our height at 50 is negative 146. Now, erasing, I've got to use more space here. Erasing all of this, we're looking at step 5. I'm going to rewrite the equation up here. Remember, just recapping, we use y equals mx plus b. This is what we're going to use in lessons following this lesson. We're going to use this trick. Okay, so instead of y, we're using a sub n. Instead of slope, we have common difference. Remember, our common difference was negative 3. So we write negative 3. Instead of x, we use n. And our imaginary y-intercept that doesn't actually exist as part of the function is 4, or I should say 0, 4. But the y value is 4, so we get the equation a sub n equals negative 3n plus 4. Step 5, again, is to find the sum of the first 10 elements of the range. Find the sum of the first 10 elements of the range. Remember, element means number, so we're finding the sum of the first 10 numbers in the range. And what is our range? We've circled it. It's the list that you were looking at the beginning of the problem. Range is 1, negative 2, negative 5, negative 8, negative 11, negative 14, negative 17. We're going to add these numbers up. Okay, so we're going to add the range values all the way to the 10th range value. So the first 10 elements of the range, and reminding you, what does this symbol mean? Sigma means what? Sigma means add. And what are we adding? We are adding what? The range. One more time, I'm going to talk to you about this concept of range. So we write, and I'm just going to erase this so that we have some space. We write, again, if I write height at 4 is equal to what? Negative 8. So if I write height at 4 equals negative 8, do you agree that negative 8 is a range value? Okay, so negative 8 is a range value. Notice, reflexive property of equality says that range must be equal to what? Range must be equal to range. So this means that a sub 4 must represent range. So notice, a sub 4 represents the range value negative 8. So we read negative 8 as range, we read a sub 4 as range, and question, what is the 4 itself? 4 itself is a domain value. Okay, so we notice in the expression a sub 4 is the range, but the domain value is what? Domain is 4. Okay? So if I write a sub n, you read a sub n as range, and you read the n as domain. We will move into functional notation where we will use f of 2. Okay? Again, f of 2 will represent range, and the 2 itself will represent domain. Okay? And f of x. F of x, the symbol will represent range, or remember that f of x is a representation of y, and x itself will represent domain. Okay, this is a much better statement than y. For instance, if we just write y, instead of using f of x, if we use y, all we see is what? Range. Y represents range, but we do not see the domain. F of x is better because we can see both the range and the domain in one statement. Okay, this is why we use f of x instead of y. But what are we saying here? We want to add the range. Now, instead of range, what symbol are we going to use to represent range? A sub n. So what are we adding? We are adding a sub n, or we are adding what? Range. Remembering that a sub n represents range. Now look at the equation again. A sub n represents range. And again, range is the same as what? Range is the same as range. But we talked about specific versus non-specific. A sub n, going back to the analogy that I used, if I tell you, well, I am a human being, that's very general. A sub n is like saying, I am a sequence. I am a sequence, or I am a human being. But be more specific. Be more specific. What human being are you? Well, I am David Thaxton. Specifically David Thaxton. So be more specific. A sub n is like saying, I'm a human. Negative 3n plus 4 is like saying, I'm David Thaxton. That's specific one. Okay, so a sub n A sub n is very general. A sub n means I'm a sequence. Okay, I am the range of a sequence. Okay, negative 3n plus 4 is what range are you? So specifically, how do we say this range? This range that's circled has a name. And what is the name of this range? The name of this range is what? The name of this range is negative 3n plus 4. Okay, negative 3n plus 4 is the name of this range. Okay, so you can, you wrote range here. You can erase range and write what? Negative 3n plus 4 is the name of this range. I guess I'm just going to rewrite range. It bugs me if it's not written. Okay, so what is the name of this specific range? The name of this specific range that you have to add is the range negative 3n plus 4. So representing range equals range, a sub n is very general. Negative 3n plus 4 is a very specific representation of this range. It is the name of this range. So what range are we adding? We're not adding just any general range. We're adding what range? Okay, so we're going to write, well, here, sigma a sub n is any range. But we need to be more specific. So what are we writing? We're writing here. I'm going to erase it. We're writing what? Sigma or add what range? That range. Okay, so we're going to use negative 3n plus 4. We read this as add what? Add the range. Now also we're adding what? The first 10 numbers of the first 10 elements. Okay, so we're going to write n equals 1 to 10. Okay, again, sigma means add. I'm going to put it down here. Add what? Add the range. And what is the 1 to 10? 1 to 10 is your domain. Okay, or the domain values. We think of this as a step ladder. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 is going in for n. 2 will go in for n. 3 will go in for n. 4 will go in for n, etc., until we get to 10. And 10 will go in for n. Now, and I'm going to show you how to read this in a minute. But right now, I need you to be able to write this. Okay, so we write what? Add. This means add the first 10 numbers in what? The range. Now let's go ahead and write those values. What does this equal? What does this equal? Well, let's just write the range values and add them up. So we have what? 1 plus, what's the next range value? Negative 2 plus negative 5 plus negative 8. Put addition. Do not put commas. We are adding. Plus what? Negative 11 plus negative 14 plus negative 17 plus negative 20 plus negative 23, plus negative 26. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can find the sum is equal to negative 125. Okay, how do you do this so quickly? How do you add all those numbers? There's a trick to this. See if you guys can figure out this trick. How do you add all those numbers very, very, very quickly? Okay, so this is a rumor. I don't know if it's actually true, but it was always said that Einstein was asked, okay, he was misbehaving in class. He was misbehaving in class, and so the teacher gets fed up with him and says, I've got to give this boy something to do. So he says, go to the back of the classroom, and I want you to add all of the numbers from 1 to 100. Okay, so thinking that this is going to cause Einstein to be busy for the next 15, 20, 30 minutes. Okay, go back to the back of the classroom and add all the numbers from 1 to 100, and Einstein takes a step and he turns around and he goes, well, isn't that 5,050? How did he do that? How did he add all the numbers from 1 to 100 in his head? Okay, he takes one step and he turns around and he goes, if I add all the numbers from 1 to 100, that's 5,050. Okay, how did he do this? Okay, so I want to see, can you figure out this trick? There's a trick here to adding these numbers very, very quickly. Okay, so you can, what can you do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want you to think about this. You may Google it. Be careful which site you go to. Some of them are quite complicated. Go to a very simple site and see if you can figure out this trick. But I'd rather you, instead of Googling it, I'd rather you try to figure it out. Okay, so see what that is. There is a trick to adding those numbers. Now, let's look at not only how to write the sigma notation, but how to read sigma notation. So before we end this video, I need you guys to step into how to read sigma notation. Okay? So we're looking at, soon, I will not be asking you to write this, but actually on tonight's homework, you're not just going to be writing sigma notation, but you're going to have to read it as a separate problem. So let's look at this. On your quiz, you have this problem, sigma n equals 1 to 10 of negative 3n plus 4. Okay, so here you don't have to write the sigma notation. The problem is given. Think of this as problem number 3 on a quiz, or problem number 3 on the test. Okay, how do you read this? Well, you know that sigma means add, and you know that 1 to 10 is your domain, and you know that negative 3n plus 4 is your range. I want you to notice something. Okay, this is actually pretty simple. This is going to be exactly the same as what we just calculated over here. Notice, we already wrote it. Okay, so we already have the answer on paper. But how do we generate this sum, or this list here? Well, we're going to plug the n values in. So I want you guys to notice, this is your range, and this is a generator of this negative 3n plus 4. You're going to see why this is the name of this specific range, because negative 3n plus 4 will give us these numbers, 1, negative 2, negative 5, negative 8, negative 11, etc. Okay? Now, by the way, I meant to say this. What are we doing here? Okay, this is not sequence. What is all this called? This is called series. Okay, and what type of series are we dealing with? Series is the sum, or add the values in the range. This is everything we're looking at right now is series. From step 5 on is series. Okay, we're adding the values in the range. Completely different from sequence. Okay, so we're adding the values in the range. Now, how do we read this? Well, we're going to put in 1. Notice this is a step ladder. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to put in 1. We're going to put in 2. We're going to put in 3 for what? For n. Okay, so n equals 1. We're going to put in 1 for n. So underneath this, I want you to write negative 3 times 1 plus 4, negative 3 times 2 plus 4, negative 3 times 3 plus 4, and let's see if we can find a pattern. Now, notice we put 1 in for n. We put 2 in for n. We put 3 in for n. We have to go all the way up to 10, but don't write all 10 of them. Okay, just write negative 3 times 1, negative 3 times 2, and negative 3 times 3 plus 4. Okay, so just write the first 3, putting 1 in for n, 2 in for n, and 3 in for n. Okay, so let's calculate. Negative 3 times 1 is negative 3 plus 4 is 1. Negative 3 times 2 is negative 6 plus 4 is negative 2. And negative 3 times 3 is negative 9 plus 4 is negative 5. And I want you to write these. So we have 1, negative 2, negative 5. And do you see a pattern? What's happening to these values? Well, hopefully you say the values are going down by what? The values are going down by 3, or we are adding negative 3 each time. Okay? Well, absolutely. They're going down by 3. Why? Because do you see mx plus b, or an arithmetic range, where our slope is the same concept as what? Common difference. Okay, our common difference is negative 3, meaning, or what is the value? What is the value in front of n? What is the value in front of n? The concept of slope, or common difference, or what is happening each time. It's going down by 3. So we can continue to write. Now just look at the pattern. 1, negative 2, negative 5, what do we have next? Negative 8, then what do we have next? Negative 11, then what? Negative 14, then negative 17. Hold on, where do we stop? Where do we stop? Well, it's nice to know where we have to stop. Either you can count them out, or you can calculate where do we have to stop. Okay, we're stopping when we put 10 in for n. So let's calculate this value. Put 10 in for n. We get negative 3 times what? Negative 3 times 10 plus 4 is negative 30 plus 4, or negative 26. So where are we stopping? We're stopping when we get to negative 26. So let's keep going. We're going to stop when we get to what? How did we figure out where we stopped? We put in what for n? The last number. We put in 10 for n, remembering that 1 through 10 is our domain. So we're going to have negative 17, go down 3 again, negative 20, negative 23, negative 26. And what does sigma mean? Sigma means what? Sigma means add. Okay, so we're adding. Okay, sigma means add, so what are we going to put between these range values? We're going to put addition. Addition, addition, addition. Okay, so we're adding. And again, you can add this very quickly. There is a trick. Okay, if you can figure out the trick, you can use it. All right, the answer is negative 125. The answer is negative 125. Now, again, what is this called? What is this called? What is this called? The sum. The sum is called what? A series. What is a series? The definition was what? A series is the sum of a set of range elements of a sequence. Or a series means add the numbers in the range of what? Add the numbers in the range of a sequence up. Add them up. So what is the series value here? What is the series? Negative 125 is the series. A series is a value. I think that's a great way to think of it. In college, it will be defined differently. A series will become will be defined as a function. It gets nasty, but we're not going to do that in high school algebra 2. Right now, you're just going to think of series as what? A value. Okay. Series is a number for now. Okay, so negative 125 in this case is the series. The sum is the series. The sigma notation can also be thought of as the series. All three of these mean exactly the same thing. So a series is a value. One more and then we're going to conclude. All right, so looking at here, just a random. Here, sigma. So how to read this? Sigma n equals 0 to 10 of 2n plus 3. How do we read this? Now, I don't want to get into this discussion. I told you guys that 0, or I should say that this was your domain. Now, hopefully you guys are arguing with me at this point. I've said all along that the domain of a sequence is a set of natural numbers. Okay, I've said that the domain of a sequence is a set of natural numbers which does not include 0. So how am I using domain value 0 here? Well, I'm not going to get into this, okay, but for series, it is okay to use 0 in the domain, okay? Series is different than sequence, okay? So series is different from sequence in that a series is not necessarily defined on a domain of natural numbers. So is it okay to put 0 in for n in a series? Yes. So if you see 0 down here, okay. Just realize, notice, I want to look over here. How many numbers are there from 1 to 10? Okay, we talked about this before. I asked you in a few videos back, how many numbers are there from 1 to 9? How many numbers are there from 1 to 9? Well, there are 9. How many numbers are there from 0 to 9? From 0 to 9 is how many numbers? Well, that's 10. So my question is, how many numbers are there from 1 to 10? Well, hopefully you say from 1 to 10, there are how many numbers? There are 10. Now, how many numbers are there from 0 to 10? There's one more. There's 11. Okay, let's count. From 1 to 10, how many numbers did we have in this sum? Well, we had 1, 2, 3, 4, 5, 6, 7, 8, 9. There were 10. Okay, let's calculate over here and see. There will be, okay, in the first one we had 1 to 10 for our domain. There were 10 values. In the second one, we're going to have 11 values in the sum. Okay, so let's go ahead and calculate the first values. We're going to put in what? 0, we're going to put in 1, we're going to put in 2. Remember, step ladder, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to put in 0, we're going to put in 1, we're going to put in 2, we're going to put in 3. For what? For n. Okay, so we're going to get 2 times what? 2 times 0 plus 3. 2 times what? 1 plus 3. 2 times 2 plus 3. 2 times what? 3 plus 3. That's enough. Okay, so by now you will easily be able to find a pattern. Okay, hopefully you can tell me what the pattern is before ever doing this. 2 times 0 is 0, plus 3 is what? 3. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7, and etc., etc. 6 plus 3 is what? 9. What's happening in this pattern of numbers? What's happening each time? It's going up by what? Going up by 2. It's going up by 2, from 3 to 5, from 5 to 7, from 7 to 9. What's in front of n? Again, what is in front of n? 2. Okay, if 2 is in front of n, the values will be going up by 2. Notice, if negative 3 is in front of n, what's happening in the series? The values are going down by what? The values are going the next value is always 3 smaller than the previous. The values are going down by 3. Okay, remember that 2 is called our common difference, so really all you had to calculate here was what? Your first value. What's your first value? 3. And if you knew that the values were going up by 2, you knew that your next value was what? 5. And your next value is what? 7. Your next value is 9. Now, we have what? 3, 5, 7, 9, 11, 13. Hold on. Where are we stopping? Okay, so how do we calculate where we're stopping? We put in the last number, 10. So let's calculate where we're stopping. Put in 10 for n. 2 times 10 plus 3 is what? 23. So we're going to stop when we get to 23. So 13, 15, 17, 19, 21, 23. And again, what does sigma mean? Do not put commas here. Do not put commas. No, put what? Sigma means add, so we're putting what? Addition.